Here we're going to look at question 15 from section 2 of the ENGAA specimen paper. So in this question we're told we have two balls, one of mass 3 kilograms and the other of mass 1 kilogram, and they're heading towards each other with velocities of 2 meters per second and 6 meters per second respectively, and they're going to collide. So this is before the collision. Then after the collision they're going to head away from one another with velocities which I've labelled on here as being v1 for the 1 kilogram mass and v3 for the 3 kilogram mass. Now we're also told that in this collision, the kinetic energy, or the total kinetic energy, is going to decrease by 25%. So this is just because it will be lost through heat or sound in the collision, or something such as that. And now with this information, the question asks us to find v1, the velocity of a 1 kilogram ball after the collision. Now if you'd like to have a go at this question yourself, then just please pause the video now. Otherwise, let's have a go at it together. So, to go about solving this kind of collision question, there are some things which we should always try and think about. So, the first of these you might be able to guess, since we're sort of told it in the question, or at least it's mentioned, and that is energy. Then the other isn't mentioned at all, but it's something we should definitely still consider, which is generally true with all collision questions, and that is momentum. So, momentum is going to be always conserved, so there's no need to worry about it ever being lost, unlike energy, which might be lost. And while still conserved in the system as a whole, it might not be conserved in the two masses colliding. So knowing this, how about we go ahead and try and consider each of these things in turn. So let's begin by considering the energy of our collision, both before and after, or our energy of our balls before and after the collision, So, before the two balls collide, they're each going to have their own kinetic energy. So, the total energy is going to be these two kinetic energies added together, where a half multiplied by our 3 kilograms multiplied by our 2 meters per second, all squared, plus, so this is the kinetic energy of our first ball, and then our second mass has kinetic energy of a half multiplied by its mass, 1 kilogram, multiplied by its velocity, 6, which is squared. So, going through and solving this, we find that this is just 6 joules for the 3 kilogram mass and 18 joules for the 1 kilogram mass. So we have a total kinetic energy beforehand of 24 joules. Now what we can do then is look at the energy after the collision. So here the kinetic energies are just going to be this. So it's a half multiplied by the mass of each multiplied by their velocities squared. Now this isn't going to be equal to our 24 joules because we're told that 25% of our kinetic energy is lost. So it's going to be equal to 75% of our 24 joules, or 3/4 of it. So, going through and simplifying this a little bit, then we find this equation here, that 3 over 2 multiplied by v3 squared plus a half of v1 squared is just equal to 18 joules. Now there's not much more we can do with energy, so how about we move on to momentum? And we can see if that's going to help us at all with the rest of this question. So, what we should do here is say the momentum before is just equal to the momentum afterwards. And to do that, we're obviously going to have to find the momentum before and after. So before, the momentum of the 3 kilogram ball is going to be given by this, and of the 1 kilogram mass will be given by this, taking account for the negative direction of our 1 kilogram mass. So while in energy the velocities were squared, in momentum they're not, so you do have to take into account the directions. Then, of course, we can find the momentums afterwards, where this time we've taken v3 as being negative since it's in this direction. The same as the 6 meters per second, which was in the same direction we took to be negative before. So then we can go through and simplify this, where the total momentum before is just going to be 6 minus 6, which will be 0. So the initial momentum is just 0, and we can solve this to find that v1 is just equal to 3v3. Now why is this going to be handy? Well, when looking at energy beforehand, we just found this equation here, which is relating v3 and v1. They're the only two unknowns. So with these two equations, we can solve them simultaneously to find a value of v1. So let's start a new page and have a look at doing that. So substituting in that v3 is just going to be v1 over 3 into this, because we want to eliminate v3 since v1 is the unknown we're trying to find. We find that our equation becomes this, which of course we can just simplify by squaring and multiplying by our fractions in front to get this here. And then since we have two fractions with v1 squared, we can just add these two together. Oops, sorry. To find that 2v1 squared over 3 is just equal to 18. Then, of course, we can just multiply by 3 over 2 to get the v1 squared is equal to 27. And then square rooting this, we get the v1 is just equal to 3 root 3. So this is going to be our final answer, the answer which we were looking for, and it corresponds with answer B given in the question.